This video is for Math 1325. We're going to be working on section 6.6 today. And the idea behind this comes from if you write the derivative of y with respect to x. The derivative of y with respect to x is dy over dx is one way to write that. That's equivalent to f prime of x is another way. That's another symbolic way to say derivative. Both of these mean the same thing. One way of thinking about these dy and dx's is they're kind of like small changes in y's and x's. Because remember that the derivative represents the slope of a tangent line. And slope is rise over run, or the change in y over the change in x. It's similar to saying change in y divided by change in x. Just like in algebra they say it that way. Change in y over change in x. So the dy and the dx represent small changes in y and x variables. A good example is that we had that problem about the icicle melting, and the volume of the ice was getting smaller and smaller as it was warming up and melting. So how does one variable's small change affect the other variable? And if you think of these individually instead of together, think about multiplying both sides of the equation by the denominator. Multiply both sides by dx, and you get an alternate version that's going to come up more in chapter 7 too. This is kind of the basis for the whole section 6.6. The derivative of y, one way to write it is f prime of x times the derivative of x. Instead of saying dy over dx equals f prime of x, just move the dx over to the other side of the equation. So they're going to give us an x value to work with and a small change in x, and then the goal is to figure out, well, how y is changing. So find dy for the given, so you know it's just dy, it's not dy over dx, just find dy for the given values of x and change in x. And the change in x, that's the same thing as dx. So y equals 3x to the fifth minus 5x. We have a polynomial function. And then we want to get exactly at the spot x equals -3. And then what if we increase x by 0.2, or even we can even do smaller and smaller values of it. So problem 1, y equals 3x to the fifth minus 5x, and then we happen to be at the x value of -3, and then we want to make a small change in x of 0.2. So the derivative of y, normally we'd say dy over dx, but I'm just going to put dy, the derivative of y, you just do the power rule normally, 15x to the fourth minus 5. This part's the derivative. That's f prime of x. And then instead of having dy over dx on this side, it's kind of like you move the dx over to this side. So I've done the derivative of y, and with respect to x is over on this side, and there's the derivative using the power rule. So this is one way to represent how y is changing as x changes. For any given difference in x, any little small change in x at whatever given x value, then I can figure out how much y is changing by. So at this point, you just plug -3 in for x, and you plug in 0.2 for dx. That's the small change in x. So dy at this exact x spot would be 15 -3 to the fourth power minus 5, and then times 0.2. So -3 to the fourth is positive 81, because that's -3 times -3 times -3 times -3. 81 times 15. 1215 minus 5, and then multiply by 0.2. So if you change x ever so slightly and increase it by 0.2 in whatever units we're talking about, if we change x by 0.2, the y would increase by 242. So this could be some business setting where we increase our production by 0.2 units in a given period of time, and then our costs or our profits or our revenue could change by $242, for example. Round to the nearest tenth is needed, but mine came out exactly, so no rounding going on. Similar kind of problem. Now I have y equals x to the third minus 4x squared plus 9. X is 1. And then what if I change x by negative 0.1? What if I decrease x a little bit? So like inflation's going on, I need to decrease my workforce a little bit to bring costs down. So y equals x cubed minus 4x squared plus 9. The given x is 1, and the given change in x is negative 0.1. So these always have to be given to you at this point. So the derivative of y is f prime of x times dx. That's sort of like a formula, I guess you can think of it as what we're doing in this section. But it's just taking stuff we had before and manipulating a little bit. So the derivative of y, which is what the answer wants, the derivative of y, you have to do the derivative of x, just normal power rule, 3x squared minus 8x plus nothing dx. So how is y going to change? If x changes a little bit at a given x value, plug 1 in for all the x's here in the derivative part, and plug negative 0.1 in for the change in x. So the change in y will be 3 times 1 squared minus 8 times 1 times negative 0.1. So 1 squared is 1, times 3 is 3, 8 times 1 is 8. That's negative 5 times negative 0.1, positive 0.5. So the y will increase by a half unit if the x decreases by negative 1/10. Type an integer or a decimal. This time it did come out as a decimal. So we had two examples of that in general first. Next up is sort of a trip down memory lane. Long ago, calculus was invented 400 years ago independently by a couple people, Isaac Newton in England, and then there was a German guy at the same time. In fact, to this day, there's argument about who did it first, but it could be that they just both did it back at the same time, roughly. Maybe one did it slightly before the other, but the world didn't have great communication back then. So people in England didn't know what was going on in Germany right away. And they each had followers that followed their writings, and then they discovered later that they both basically did it at roughly the same time. And nobody to this day knows who really did it. But that was well before the era of calculators. Now with calculators, we can easily do something like the square root of 103. But the calculator is actually using a program that's based on this section right here, actually. So back in the day, before calculators, they used this technique of approximating hard things like square roots or logs, or if they didn't have a calculator, obviously. Today, this is kind of obsolete, but they just want to show you what's going on here. This is kind of what your calculator is doing behind the scenes, really. So use the differential to approximate this expression, then use a calculator to approximate the quantity and give the difference between the two results. So square root of 103 I would like to do square root of 103 without a calculator. Well, that's like saying that the function is square root of x. I have a general function of square root of x, and then we can write that as x to the 1/2 because we're going to end up doing a derivative of it in a second. It'll be easier to do it with the power rule than with a square root in there. So you just take whatever your function looks like and put kind of like the parent function of it, the most basic version. And then the trick to doing this is you want to get a value as close to 103 that comes out evenly. The closest exact square root to 103 is the square root of 100. The square root of 100 equals 10 exactly. So I want to use 100 arbitrarily for x. And then my dx is going to be the change in x. How did x change? X went from 103 down to 3. I changed from 103 down to 100, so my change in x is 3. I'm off by 3 units. So once you pick your x, you figure out how far away you are from that. And now you're going to do like the first two problems. The change in y, the answer, will be the derivative of x times the change in x. Same idea as problems 1 and 2 once you get to this point. So what would be the derivative of x if my original function is x to the 1/2? It would be 1/2 x to the 1/2 minus 1, or negative 1/2. And then you could write that a couple of different ways. I could put the x down in the denominator and make it positive 1/2. And then because I'm going to be plugging numbers into it, I would probably put it back as a radical. Thus, x to the 1/2, same thing as square root of x. So the change in y will be the derivative of x, 1 over 2 square root of x times dx. This is what I'm going to be working with kind of in generic form first. So now you can plug in 100 for x, since that was the chosen x that's close to the 103. And then you can plug in 3 for the change in x because you're off by 3. The square root of 100 is 10. That's why we chose that, so that would come out exactly. Square root of 100 is 10. 10 times 2 is 20. So I'm going to get 1 over 20 times 3. And then 0.15. Let's see here. Okay, so I don't think I'm doing this right. Change in x. Okay, so maybe it isn't this actually. I'm getting this mixed up. This isn't it. Because I can already tell this equals 0.15. It's not going to equal what the square root of 103 is close to. We're supposed to get 10 see, 0.15. There it is right there. So I guess this isn't exactly the same thing. So what's actually going on here is you're doing f of x, and then you want to add a little bit of change in x. So I want to line this up with f of 100 plus 3. Like this. That's how the 103 happened. F of 103 could be written as f of 100 plus 3, because 100 plus 3 is 103. And then this will be an approximation. So it's f of x plus, see, this is what it is. Yeah, I just found the dy. dy is 0.15. That's the part that's like problems 1 and 2. So this was like problems 1 and 2. You do this first, but then you have to add it back to what you started with, the one you picked out. So the square root of 100, f of 100, the square root of 100 was 10, and then my dy was what I just calculated, 0.15. So it's one step extra than the first two problems. In the first two problems, I just found dy. So if x changes a little bit, how much does y change? Y changed a little bit too, but then I have to add it back to what my approximation, my chosen value that was exact. So this would make the answer 10.15. This gives you a quick approximation. The square root of 103 is approximately 10.15. And then we can know from a calculator that it's 10.14889. See, that's pretty close. 10.148 is pretty close to 10.15. What is the value? Okay, so round to 4 decimal places. The value I got was 10.15 exactly. There was no rounding going on. And then what is it? 4 decimals in a calculator. That's 10.148. And then this 8 would get bumped up to a 9. So those are pretty close to each other. 10.15 versus 10.1489. In fact, if we rounded this to 2 places, it would be 10.15. What is the absolute value of their difference? So that's where you just subtract their difference. And if you get a negative, just ignore it. Whoops. Although there it is. Okay. So just ignore this negative. The absolute value means what's the distance away from them. How close is this to 4 decimals? It's only off by 0.0011. 0011 is the difference it's off by. That's a pretty small difference. And see, the calculator can do it much closer than we're doing it. So that's why this is kind of the basis on how calculators calculate these things. But they can get closer and closer and closer, much closer than what we could do by hand. And that's how they do it faster. So that's how they get the approximation better than we're getting it. But for hundreds of years, this is how they would approximate square roots or logs, which are hard to do by hand. So number 4 is similar to number 3. Now I want to approximate a natural log of 0.96. And the closest one that comes out exactly to that is one that many people from algebra know as a property. In algebra, we know that the log of any base of 1 equals 0. And it's because log graphs go through the point 1, 0. 1, 0 is a key point on a log graph. So when the domain is 1, the range is 0. Log of any base of 1 equals 0. And notice this is pretty close to 1. So just like the square root of 103 is close to the square root of 100, you want to do some log that you're close to. Something close to this that comes out exactly. So first find your dy. dy is f prime of x dx. This is what we do in the first 2 problems. And then this gives you the change compared to your answer. So dy here would be, the original function is just natural log. So f of x is natural log of x. The derivative of that is 1 over x. That's one of the derivative rules we learned back in chapter 4. The derivative of x, of natural log of x, is 1 over x. Okay, so then I'm going to be plugging in, I'm going to use x equals 1, just like before we did x equal to 100. Here, where did I write it? X equal to 100, that was the convenient number. And then the delta x is when you take what you want to do minus what you find convenient. So for me, x is 1 because that's the convenient one. And then delta x is the one you started with minus the convenient one. So I'm changing x by negative 0.04. There's a negative 0.04 difference between what I actually started with and where I'm at now. So we're going to plug 1 in right there, and we're going to plug this in right here. So dy equals 1 over 1 times negative 0.04, which the ones are convenient, makes that negative 0.04. But then, this is the key to finishing these problems. The f of x plus your little bit of change, f of x plus a little bit of change in x. This I'm trying to get f of 0.96 is what I'm really trying to do. I want to do 0.96. Well, we can think of 0.96 as 1 minus 0.04. 1 minus 0.04 is 0.96. And that's this dy here is the minus 0.04. So then you're doing your f of x that came out exactly. The one that came out exactly, here it was 10. And then you add whatever the y changed by, or subtract in this case. So f of 1 here, f of 1 is 0 right there. I picked 1 on purpose because that one came out exactly. So f of 1 is 0, and then you minus your little dy. Or add. Normally it's adding, but adding a negative, same thing as subtracting. So then I would get that this is negative 0.04. So doing this with calculus, the approximation is negative 0.04, and that was all done without using a calculator. Negative 0.04 is the by hand method using calculus. What does the calculator say the answer is? What is 0.96 ln? Look at that, negative 0.04. See how close it is? It's not exactly that, but it's negative 0.0408. That's a pretty close approximation. If you round to 3 decimals, it's only off by a thousandth. So what's the absolute value of the difference? Just take either answer and minus the other one. Minus 0.04. If the answer comes out negative, just ignore the negative. So the difference is 0808. Okay, so let me try that again. Type one of them in there. 0.04 negative, and then you minus, oh, I know what I did wrong. I didn't put minus a negative. Minus 0.0408 negative. Minus a negative, actually. So the difference is 0008. That's a pretty small difference. 0008. Tenths, hundreds, thousands, 10,000. So it's a 8 and 10,000 difference. So that's pretty close right there. So 3 and 4, they're kind of applications of 1 and 2. 1 and 2, you're just finding the change in y. In 3 and 4, you're finding the change in y first, and then you're adding it back to your approximate one that was close. Okay, now we're going to do this for business and real life settings. The demand for grass seed in thousands of pounds at price $P is given by this function. Use the differential to approximate the changes in demand for the following changes in price. So what if price changes from $3 to $3.14? So I have a demand function, d of p, negative 3p cubed minus 2p squared plus 1461. And we're going from $3 to $3.14. The price just changed. How's that going to affect demand? Whoops. I had to write the 4 before the 1. Okay. Okay, so think of, I want to do the derivative of demand. That's like the y variable. What we're trying to do here is this here, but in these other variables. The derivative of demand is the derivative of price times the small change in price. Derivative in demand is the derivative of price times the small change in price. That's what this whole section's about. So the derivative of demand, I can do the derivative of this with the power rule, negative 9p squared minus 4p plus 0, and then dp. This is what it is in general. Okay, so we started at a first price of $3. This is what P was. And then it switched to a second price, $3.14. So the original P is always the first price. That's kind of like the 100 in the square root problem. And then it changed to like 103. So that's what it changes to. That's where the dP is going to come from. So dP is always the second thing you end at minus where you started. So 314 minus 3, there was a change in price of 14 cents. And it did go up in price. That makes sense that that's positive. The price increased by 14 cents. What happened to demand because of that? So put 14 here and put 3 in for the P's. The change in demand, the derivative of demand, the change in demand is negative 9 times 3 squared minus 4 times 3 times this increase of 14 cents. So 3 squared is 9. 9 times negative 9 is negative 81. 4 times 3 is 12. Negative 93 times 0.14. And this actually makes sense already that the answer is going to be negative, because when price goes up, demand goes down. That's the law of supply and demand in business. So 93 negative times 0.14, the demand goes down by negative 13.02. There's a decrease of 13.02 in demand. The change in demand by a change in P from 3 to 314 is about, type in integer or decimal, and this is in pounds, and this is in thousands of pounds. This was already in thousands. So decimal, so I'm going to put the whole thing, negative 13.02. And then the good news is about part B, since all this different is the prices are different, I have to redo all the derivative work. Not that that took all that long, but basically the only thing different in part B is that price is going from $5 to $5.19. So you only have to repeat from where you plug numbers in. This derivative is still the same. So right here, instead of putting 3's here, I'm going to put 5's. The first price, the first value is always the P variable or whatever variable you're working in. And then the dP is the second price minus the first price. This shows what it changed by. Price went up 19 cents. So the change in price is 0.19. The original price was 5. How is that going to affect demand? If the original price changes from 5 and goes up by 19 cents, what demand's going to go down by something, obviously. So plug in 5's in these two slots. The change in demand is negative 9 times 5 squared minus 4 times 5 times this 0.19 change in the price. So you're just recalculating with new numbers instead. So 5 squared is 25. 5 squared is 25. Times -9 would be -225. 4 times 5 is 20. So -245 times 0.19. -245 times 0.19. The demand will go down by 46.55 units. Pounds, I guess is what that is. Thousands of pounds, actually. -46.55. Okay, here's one about a population. The population of bacteria in millions, and luckily the answer wants millions, in a certain culture, X hours after an experimental nutrient is introduced to the culture. We got this rational function right here. So same kind of deal. We want to know if the time changes by a little, if we change X a little bit, if we change the time a little bit, how will the population be changed? So change the time from 1 hour to 1.5 hours. How many millions more bacteria will there be? So we're starting with a population function. The population based on time is 30x over 5 plus x squared. And part A is going from 1 to 1.5. And then there'll be a part B where you'll just have to repeat the last steps of plugging it in. Okay, so we want the change in the population. How does the population change? It's going to be the derivative of the population times the change in the hours, which are x here. They could have put t for time, but they chose x for some reason. Okay, so first I'm going to need to know what's the derivative of the original function. And then dx is going to be 1.5 minus 1. The second one minus the first one, 0.5. 0.5 is dx. That's always the easy step. So the time is changing by half of an hour. How does that affect the population? The time is increasing by half of an hour. And you're eventually going to plug 1 in right here, but we got to figure out the derivative first. So the derivative is, maybe I'll do this on another page. This is going to be a quotient rule, unfortunately. 30x over 5 plus x squared. We got a function of x divided by a function of x, so good review of the quotient rule. Second times derivative of the first. Derivative of the first is just 30 minus the first times the derivative of the second. The derivative of 5 is nothing. The derivative of x squared is 2x over the second squared. So we don't probably have to simplify this too much because we're going to be plugging x in. But let's see if it simplifies a little bit. 30 times 5 is 150 plus 30x squared. And this is 60x squared right here. So minus 60x squared. And I'll just do this because I'm gonna write it one more time. So I could put 150 minus 30x squared. That's what the numerator simplifies to. The denominator is 5 plus x squared squared. but there's no need to try to simplify this any further. Maybe it reduces down even further, but there's no need to even waste time doing that. So I got it at least simplified a little so that plugging into it isn't too messy. But now there's the derivative. So 150 minus 30x squared, 150 minus 30x squared over 5 plus x squared squared dx. This is the setup in general. So now we're ready to plug 1 in for all the x's, and we plug 0.5 in for dx. So the change in population after we started at 1 hour, we started counting at 1 hour. And then a half an hour later, time had changed by a half an hour. We had a small change in x. What happened to the population? So 1s are nice to plug in. 1 squared is 1. 30 times 1 is 30. So the top is 150 minus 30, 120. 1 squared is 1, plus 5 is 6. 6 squared is 36 times 0.5. So the population is going to change in millions by whatever 120 divided by 36 times 0.5 is. And how do they want the answer? Round to 3 decimal places. So 1.667 million. It went up by 1.667 million bacteria in just a half an hour. Almost 2 million. Closer to 2 million than 1 million. So then the only difference on part B is your delta, your dx changes. 4.25 minus 4. 4.25 minus 4 will be dx. 4.25 minus 4 is 0.25. And x is 4 now instead of 1. So if we start when x is 4 hours and then we wait a quarter of an hour later, how much has it changed from that point? So now you plug 4 in for all the x's and you plug 0.25 in for that. So 150 minus 30 times 4 squared over 5 plus 4 squared, and then times your 0.25. So not quite as easy to calculate this one, but let me move it here. Okay, so 4 squared right there. 4 squared is 16 times 30 is 480. For this part right here is 480. 150 minus 480. The numerator is negative 330. 0.25 over here. And then the denominator, we're going to get 4 squared 16 plus 5 is 21. 21 squared for the denominator is 441. Okay, so I guess I was wondering why it's negative, but I guess the population doesn't have to just keep growing forever. It must, at some point, it must have slowed down and started decreasing for whatever reason. So negative 330 divided by 441 times 0.25, negative 187. So it's about 200,000, a little less than 200,000, round to 3 decimal places. So the population decreased by almost 200,000 for some reason. And if you have a rational function, it could be going up at some point and down at another point. So that was the only weird thing, is how did the population start decreasing suddenly? But maybe there's so many bacteria they start fighting with each other and killing each other off or something. But yeah, it starts going down after a while. Okay, then here's more bacteria in a petri dish. Now, the shape of the bacteria on a Petri dish is circular. Find the approximate increase in its area. So we're doing circular area. If the radius increases from 30 millimeters to 32 millimeters. So there's your change in x. Your x is changing from 30 to 32. We've got circular area. That's a very basic formula from geometry, pi r squared. So they didn't give me a formula because it's a very obvious one from geometry, they think anyway. And then we went from 30 to 32. So the first number that you start at, that's the main variable, that's r. And then if you take both of them and subtract, that's dr, the change in r. R is changing from 30 to 32, so it's increasing by 2. Always do the second one minus the first one to get the change. So the radius started off at 30, and then it increased to 32 as the bacteria is growing in a circular fashion. So what is the change in area as the radius changes? So the change in area is the derivative of area times the change in the radius. That's the main formula we're using on almost every problem. Okay, so change in area. Luckily, the derivative of area, this is just a power rule because pi is just a constant. So same thing if you had like 3x squared, you would do 3 times 2 for the constant in front. 2 times pi is literally 2 pi. R to the 2 minus 1, which is 1. So the derivative of the area function, pi r squared, strangely, that's the circumference formula from geometry, 2 pi r. So just leave pi in the answer. Don't plug anything in for it unless they want a decimal answer. They usually like pi left in the answer when this occurs. Change, or not change, but plug in 30 for r, because that's what the radius started off at. And then plug in 2 for dr, because that's what the radius changed by. It increased by 2. So 2 times 30 is 60, times 2 is 120 pi. Now we know pi is about 3.14, but you don't want to do times 3.14 unless they specifically ask for it. But you could do it for your own purposes and say, if the radius increases by 2, then the area increases by almost 400. But I think they're going to want 120 pi for the answer, not 370, whatever. But always read the blue part to know how they want the answer. They'll count it wrong if you put 376.8. Because it says type an exact answer in terms of pi. So they want you to leave pi there, and you can either hit this pi button right here in the toolbar, or if on your keyboard, if you type the letters P, I, it switches it to pi. So you can do it either way. But this is just another application problem of what this section is about. If you want to change one variable, it depends on the change of the other one. A spherical snowball is melting, so the sphere's volume is getting less and less volume. Find the approximate change in volume as the radius changes. See, there's two things affected by each other. The volume is changing as the radius is getting smaller and smaller. And if it's warm outside, the snowball will melt. So as it gets smaller and smaller and smaller, the radius, at the moment in time we started keeping track, the radius was 3 centimeters and it decreased to 2.6. So you would have to know the area, or not area, the volume formula from geometry, volume of a sphere. Volume of a sphere, you might have to look that up, but the volume of a sphere in geometry is this is a weird one, 4/3 pi r cubed. Maybe you remember that, maybe you don't, but 4/3 pi r cubed. So we want to do the change in volume. How is volume changing? When I'll call this V of R, just to have a function notation for it, V of R. the volume in terms of the radius. So the change in volume is the derivative of volume times the change in the radius. That's the main formula we've been doing the entire section, basically just another format of this. And then only the problems 3 and 4 where we're approximating radicals and logs, then there's a slightly extra formula that you do to the end of those problems, because you have to go back to the original and then add the change. But that only happened on problems 3 and 4. Every other problem is just using this main idea right here. So we had a starting radius of 3 centimeters. It decreased to 2.6. The radius started at 3 centimeters. So that's going to be the R, the radius. And it decreases to 2.6. So the change in R is the second value minus the first value, even if it comes out negative. It should come out negative if it's decreasing. The radius is getting smaller and smaller and smaller. It's decreasing by negative 0.4 at this moment. So that's what's going to go there. That's the easy part. Do the derivative of this. The derivative of 4/3 pi r cubed is 3 times 4/3 pi. Those are all the constants right there. And then you decrease the exponent by 1. And conveniently, the 3's even cancel out. So the derivative of 4/3 pi r cubed is 4 pi r squared. And we're going to leave 4 and pi alone. They're constants. Plug in r of 3. And plug in negative 0.4 for the change in r. 3 squared is 9. 9 times 4 is 36. 36 times 0.4 negative is negative 14.4 pi, if they want pi left in there. So the volume is it's decreasing by 14.4 pi units. Now maybe because, see how, since 14.4 has a decimal, that's why they want the answer in decimals. Round to the nearest tenth as needed. Round to the nearest tenth. So that's when you can plug in pi. But don't just use 3.14. That might not be enough of approximation. 3.14159. If you're going to do a decimal, use that much. Some calculators have a pi button on them, actually. Like this right here. See how 3.14159, and then it goes on and on and on. If you have a pi button, use that because you'll get a more accurate answer. Pi times 14.4 negative. So generally the rule is when the answer comes out as an integer, they leave pi in the answer, but if the answer has decimals in it, then they'll let you plug decimals in. And they wanted nearest tenth. So that is negative 45.23 or negative 45.2. Negative 45.2. So if the radius decreases from 3 centimeters to 2.6 centimeters, the change in volume will be decreasing by 45.2 cubic centimeters. If I would have done 14.4 negative times just 3.14, sometimes if you just round this to 3.14, sometimes it's enough to be off. Here it would have still been the same, but it's only 45.21 instead of 45.23. It makes a little bit of a difference. If you round it to 2 decimal places, they would count it wrong if you're only using 3.14. So everybody associates pi with 3.14, but if you can use more decimals than that, that definitely helps. Okay, so a lot of word problems in this section. There were only 8 of them, luckily. So we'll save that and got 100 on that assignment now. That's the first of 6 assignments that remain in our fourth and final unit. So we just completed test 3. And now we're in this final unit here, 6.6, and then we're going to be doing 5 sections of chapter 7. And then there's a review for test 4, the last regular review. That's due on December 9th. All these are due December 9th. That extra related rates homework assignment, that's due December 9th as well. And at that point of the semester, we'll have 1 week remaining to take the final exam. So we'll have a week of reviewing and taking the final. 7.1 has 12 questions when we do that video. So that the first 6.6, each problem takes a little longer. So I put 8 there, and then these go a little faster. So now there's 12 here. And that way we'll be back on pace of an average of about 10 problems per assignment. So in chapter 7, we're going to do what are called antiderivatives. It's the opposite of a derivative, actually. Antiderivative. There's an opposite of a derivative. And then we'll learn different rules about them in the remaining 4 sections after that. But things will start getting backwards now when we do antiderivatives. And there's an application to antiderivatives. They find area. Derivatives find slopes of tangent lines. Antiderivatives find area. And you can just do area under a curve, or you can do area between 2 curves. That's 2 applications of it, actually. So that's what's coming up. So we're done with the first of 6 sections in the final unit to do. And then we'll have 1 more section this week, and then we're supposed to do 7.2 in our half week next week, but I'll get these all done and sent out to you. So if you want to finish them before next week, you won't have to do anything during the Thanksgiving week. See you next time for section 7.1.